Hi, I'm Norman Wahlberger. Today, let's consolidate our understanding of this new geometry, red geometry, that we introduced in the last video. This is a relativistic geometry in 2 dimensions, and it has many new features that are quite different from ones that you've seen before. So, our setup is, we're working in the grid plane, points as usual, lines as usual, except we're using the idea of red quadrants. So to remind you what that is and to illustrate it in a special case, here are 3 points A1, A2, A3, point 2, 1, 3, 4, and 8, 3. Let's talk first about the quadrants between A2 and A3, which is Q1. So we're talking about a red quadrants here. How do we calculate that? We take the difference between the x coordinates between A2 and A3, which is 5. We square that. And we subtract the difference between the y coordinates, which is minus 1. Square that. So we get 25 minus 1, that's 24. I'll leave it to you to figure out that Q2 and Q3, this red quadrants here and this red quadrants here, are 32 and minus 8 respectively. Now let's calculate some spreads. For that we need some lines. So the line L1, the line between A2 and A3, this one right here, its form is 1 to 5 to minus 23. You get that by looking at the points A2 and A3 and using the join of points theorem. Here's the form for L2, here's the form for L3. If we want to calculate the red spread between L2 and L3, which we're calling S1, what do? We take these 2 expressions here, and we first of all have a minus sign, and then it's minus 2 times 1 minus 3 times 6. Altogether minus 2 plus 18, and all of that is squared in the numerator. In the denominator we get minus 2 squared minus 6 squared, or 2 squared minus 6 squared, and multiplied by 3 squared minus 1 squared. When we work that out, we get 1. A spread of 1 is perpendicularity, telling us that these 2 lines, this one here and this one here, are actually red perpendicular. Similarly, the spread S2 between this line and this line is 4/3, and S3 you can calculate to be minus 1/3. The kinds of phenomena that we're familiar with for right triangles in blue geometry, in our familiar Euclidean geometry, are also holding here. Such as, well, first of all, Pythagoras' theorem. Q3 plus Q2, the sum of these is equal to Q1. That's Pythagoras' theorem, because in this context, this is the hypotenuse side. It's opposite the right vertex. And I also point out that this is a right triangle in the red sense, and so these 2 spreads here, S2 and S3, do in fact add up to 1, just like they do in blue geometry. Let me make a few important remarks about this red spread. Let's go back to a general line L1 and a general line L2 with coordinates like that. And I recall that the red spread between them is minus A1 B2 minus A2 B1 squared over A1 squared minus B1 squared times A2 squared minus B2 squared. That's the red spread. Now you may wonder, why are we having this minus sign here? And I want to explain in a way why that minus sign is there. It comes about by looking at 1 minus s instead. If you take 1 minus this expression, then you're going to get 1 plus this quantity here. And if you take everything over a common denominator and simplify, and this is a very important exercise for you to do, so please do this. I take 1 minus this expression, simplify it, and convince yourself that you're going to get exactly this expression. A1, A2 minus B1, B2 all squared over these 2 things. This is a red or relativistic analog of what we called Fibonacci's identity previously. And this quantity here is of independent interest. It's called the cross between the 2 lines. So we can call it, in fact, the red cross to distinguish it from the blue cross. In the numerator of this red cross, we have the algebraic equivalent of being perpendicular. So the two lines are perpendicular precisely when this numerator is 0. That's the same as when s equals 1. Here's another important observation. These two lines have certain directions. And the directions can be deduced from the form of the equations. This equation here has direction minus b1a1, and this one, L2, has direction minus b2a2. And the observation I want to make is that the spread between these two lines can also be computed by using this formula applied to the two direction vectors. In other words, you take minus this times this minus this times this, all squared, over this squared minus this squared times this squared minus this squared. And the quantity that you get is easily seen to be exactly the same as this one, because the two minus signs here are the same, and this is just a rearrangement of that. So this is an important observation that makes computing spreads easier, because finding vectors is generally easier than finding the equations of the lines. Let's have a look at how it works in a more general example. So here's an example with the point A1 equals 2, 6, A2, 4, 1, and A3, 8, 3. There are points right there forming a triangle. And now I'll let you make the calculations that the three quadrances are 12, 27, and minus 21. The vectors joining the points are given by these expressions. And then applying the formula on the previous page, for example, S1 is the spread between these two directions. So we get 2 times minus 3 minus 6 times minus 5 divided by 2 squared minus 5 squared times 6 squared minus 3 squared, over 64 over 63. And the other spreads you can calculate are 16 over 7 and minus 16 over 9. So what are the relationships between these three quadrances and these three spreads? Well, the relationships are that they are exactly the same as the relationships in blue geometry. In other words, the trigonometric laws are exactly the same. Word for word, letter for letter. And I want you to check that. I want you to check these laws and see that they are actually satisfied with these values. Let's have a look at some geometry that comes out of this new picture. Here's our triangle, and I've shown you a few other things. I've shown you the midpoints and perpendicular bisectors. So at this point here, for example, I've shown you in green the line which is actually perpendicular to this one, perpendicular in a red sense. And right here, there's the perpendicular bisector going through that midpoint, and here the perpendicular bisector there. And lo and behold, the three perpendicular bisectors meet at this point here, which is the analog of the circumcenter in blue geometry. In fact, it's exactly the center of the unique circle that goes through the 3 points. But a circle has to be interpreted in a red sense. In other words, it becomes a hyperbola. And I've given you an indication of that hyperbola there. We'll talk more about that in later times, but I think it's good to see that already initially. The centroid of the triangle, the intersection of the medians, is exactly the same as before, because a median and a midpoint are independent of metrical issues. That's an affine notion. I'll leave it to you as another exercise to show you that the orthocenter, the intersection of the altitudes, actually exists. The three altitudes meet at a point somewhere up there. And you can try to convince yourself that those 3 points, the circumcenter, the centroid, and the orthocenter, are all collinear, just as they are in blue geometry, forming the Euler line. And in fact, even moreover, this to this is in the ratio of 1 to 2, just as it is in ordinary triangle geometry. So you can see that we're moving now into really new geometry. These are things that most mathematicians don't know. And there's a whole range of fascinating phenomena that becomes visible once you have these tools of rational trigonometry in this red setting. Next time, we are going to look at these laws of rational trigonometry in the red setting and prove them. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.